Good afternoon, everyone. I'm presenting this new visual place recognition research on behalf of my PhD student, Surav Garg, who couldn't be here, as well as my colleague Nico Sunderhoff. We're from the Queensland University of Technology. So this slide encapsulates the problem. We're trying to take the visual place recognition problem up one more notch. So this is a car, it's driving down a road in opposite directions, it's got a limited field of view camera, and conditions have changed from day to night, about as extreme an appearance change as you can imagine. And we're trying to create a system that can recognize that this is the same place with this limited field of view camera under these extreme appearance changes and combine all these problems for the first time. So during the daytime, this is tough enough. This image shows the same place from opposite viewpoints, and you can see that some of the landmarks are commonly observable. Their geometry looks a bit different, but some parts of the scene are just not commonly observable from different viewpoints when you have a limited field of view sensor, such as a camera. And that's hard enough, but when you add extreme appearance change on top of that, such as from a day-night cycle, this problem becomes pathologically difficult. And to the best of our knowledge, this is the first time people have attacked all of these problems simultaneously. This is from the Oxford Car dataset. Now, if you're a self-driving car company, you don't solve the hard problems that you don't need to solve. So you use a 360-degree sensor. You might use a LiDAR sensor, a panoramic camera, something that explicitly binds the forward direction to the reverse direction. One of the beauties of being in research, I guess, is we can afford to go after some of the interesting hard problems which aren't necessarily directly on the critical path to an autonomous car. There are, of course, other reasons to investigate this problem as well. We know that humans are able to drive in reverse along a road for the first time, perhaps coming back at night, and recognize where they are. And we know that humans don't have a 360-degree sensor, and we know that humans aren't constantly looking in their rearview mirror, yet they're able to know where they are. And it's likely that this depends on semantics, a richer understanding of the world. And that's what we emulated in this research. So if you look at visual place recognition research, it's got a long history. It started off with handcrafted approaches, and it's moved into deep learning approaches, end-to-end learning approaches, and increasing use of semantics. And you can think of this work, this research, as extending upon that trend of bringing in deep learning and bringing in semantics into your pipeline. Our approach is fairly straightforward. We use some dense semantic segmentation to compute a local semantic tensor. That's how we got that acronym very painfully out in our paper title. We also perform some spatial verification as well, just to make the performance a little bit better. This is an example. You perform dense semantic segmentation. We're only interested in 3 classes, and you extract descriptors from the Con5 layer of the network for each of the pixels for each of the semantic classes. Now, you don't just do this for one image. You do it for all the images in your database as well as your query image coming from the camera. We then calculate mean tensors for each of the semantic classes, and then we subtract each of the descriptors from the images from these mean tensors to create a mean absolute deviation tensor, and then we concatenate that for the 3 semantic classes we're interested in to create the local semantic tensor. And this is the key representation of the image we use, and this is how we get our initial candidate image matches in our system. But because the problem is so challenging, we have to add extra stuff on top of that. So what we do is we use the activations of the feature maps in Con5. We look at the regions of the image where they're maximally activated, and we use these to speculatively form key point correspondences between the 2 images we're comparing. Now, doing that with real-world imagery this tough is going to lead to lots of spurious key points. So what we do is we perform some filtering on top of that. We filter out key points that don't belong to the same semantic class in both images, and then we do a weighted key point comparison where we look at the distance between the key points in image space, but we also look at the distance between the descriptors associated with those key points. And that enables us to provide our final image match hypotheses to perform visual place recognition. Now, if you put all of that together into a system, this is what happens. So this is the hardest data set that probably exists at the moment. This is the Oxford Car data set in opposite directions on day-night. And on this precision recall curve, we're able to achieve good performance. NetVLAD, which is an incredibly capable state-of-the-art system, even with temporal filtering chucked on top of it, is unable to solve it. But this is our system solving it, recognizing these places from the opposing viewpoints with a limited field of view camera under extreme appearance change. So the conclusion, I guess, is that semantics alone and geometry alone are not enough, and when you combine the 2 together, it really enables you to take your perceptual performance up to the next level. Thank you very much.
Okay, there's a question up there. Yep. Yes, I had a question for the presenter of Lost. So that was very interesting that it can detect 180-degree places. That's definitely novel. But I had a question about, is your system fast enough for online use?
The slowest part by, I think, about 2 orders of magnitude in the current very unoptimized system is the segmentation part. We do discuss in the paper we could swap it out with a more approximate segmentation technique, achieve real time. It's definitely not real time at the moment, but you could get to real time fairly easily, we think, with only a minor degradation in overall performance. As you saw, there's multiple stages of the system, and the segmentation is important, but the spatial verification check, as with a lot of other past work in this field, is equally important. So a slight degradation in the actual quality of the segmentation, we don't think would have particularly adverse consequences.
Thank you.